Thanks very much for the opportunity to talk about return times. So I'm all wired up in this futuristic outfit, so I don't have to talk so loudly. So what I want to talk about is return times, so which means you're given a map and a t-invariant probability measure. Then out of this omega you cut out a piece, some u, and you define what's called the return time function. So you take some u, which is in there, and show me non-trivial. So that's the first time any point either enters, or if it starts inside, you return. So that's the minimum or the infimum of all j bigger equal 1, so you enter for the first time, or you return, so bigger equal to this. Well, Edward Noyes Poincaré from 1899 said that tau sub u is finite for almost every x in u, provided mu is a finite measure. And then this got a little bit more precise from 1947 by Katz, who then said that the tau u, if we restrict to x in u, is roughly this, on average, that is. Well, to be precise, this is 1. That's where it comes from. So, and we are of course interested in how is this distributed, because it naturally is not equal to this value there, or anywhere close in some uniform fashion. So what one wants to do is one wants to have u go to 0. What it means is that the measure of u goes to 0 somehow. One has to be a little bit careful about that, because there is an example by Lacroix and also Kupser from about 10 years ago or so, which says the following thing. If you are given some reasonable distribution function, so something which goes somehow towards 1, not too bad, but pretty arbitrary, then, well, and mu is ergodic, so given mu is ergodic, then there exists a sequence of sets un, so that un goes down to 0, and that if you look at the probability of un being bigger or equal t over mu of un, and that of course is exactly the scaling which comes from Katz's formula there, well, this converges to f of t. So I need to make a mistake. Maybe I should have put it the other way around, lesser or equal in that case. Then it goes to f of t. And of course, these are wild sets. They're constructed in some way, often typically completely disconnected. So one has to put a condition on what the uns are. And the conditions is to, so to get meaningful results, need some regularity. And there are typically 3 cases that are being considered. Namely, un are cylinders given some partition, or unions of cylinders. Then UNs are metric balls, or UN could be dynamic balls. So we'll say something about these first 2. The third one, Fan Yang talked about last week, so I won't say anything about this, but there are similar results that hold true under suitable conditions. So let's look at the cylinder part. And the reason I have to talk about cylinder for metric balls is because currently practically all the results of metric balls involve cylinders. So we have to go through cylinders no matter what, at least as in the current state. So for cylinders, you take a partition and you form the join. So that's the nth join. So these are the cylinders. We assume A is generating, which means A infinity consists of singletons. So which means you don't have patches traveling around. You only want to cut down everything to single points ultimately. And then our general notation will be A sub n of x will be the unique cylinder which contains x. And because A sub n is a partition, A n to the n is a partition, this makes really sense. Well, then there is a result by lots of people in various versions. But what happens is, well, it was Schmidt began this as Abati. Werner, I believe. Who else? So maybe. Hirata. Did I forget anybody? Hopefully nobody who is here in the room. Which is, if you look at the probability of a cylinder coming back to itself and you scale it, I don't want to be too precise about this point, then this goes to e to the minus t. There sometimes has to be a slight scaling factor. You have to adjust the time just so ever so slightly. Then this goes to infinity as n goes to infinity. This goes through the exponential distribution. So it's decreasing. It looks like this typically. That's e to the minus t, and you begin at 1 here because you've put in 0. Well, this is if, and this is for almost every x. If mu is psi mixing, that was the original result of Schmidt. Phi mixing, or alpha mixing. And you get various other terms in these different cases, and of course in decreasing strength as you go down there. I don't want to say too much about, I don't want to say anything about periodic points, but you have to exclude them, of course, get different distribution there. We have a mass sitting there, and then it decays, it drops off lower. So that's, I think we heard about something about this yesterday. Well, maybe I should say something about the mixing properties. So psi mixing, mu is psi mixing, that's the best kind, that's what the original result is. When you take an intersection of reasonably nice sets, which is cylinders of a suitable kind, and you compare them to what they should be in the end, then this can be uniformly bounded. If it phi means that if you condition on only one of those, say the left one, this goes to 0, and alpha would be that if you look at, why do you write phi? It should be mu. If we have mu of b, t to the minus n minus k, c, towards what it should be in the end, if this goes to alpha of k, which goes to 0, and b are cylinders or unions of cylinders, of n cylinders, c is anything in the form of sigma algebra, and this is for all n and k. So here is b living on coordinates from 0 to n, if you do it in symbolic way. Then the pullback, you pull back, of course, n, and you open up a gap k, and then the t to the minus n minus kc is living somewhere here. And doesn't matter how far you go out. So you have this gap k, and that gap k determines what your decay rate is. So under these conditions, you get this exponential distribution, and there are even error terms here, so there are many various possibilities. The hierarchy of mixing, of course, as you can see, is downhill. So psi involves phi involves alpha. Here you find typically nice system axiom A, Anosov. You find also rational maps and suitable equilibrium states, maybe with a slight weakening here. Over there, you would have Young towers, and I will talk about this later on again. The middle is not so much populated, but there are some renewal systems in there. That have this property in alpha mixing. So what I actually want to talk about now is what happens if you don't just wait for the first return, but you wait for higher order returns. So you introduce a counting function. So again, you let, say, u be in omega, and of course positive measure to make it meaningful. Then you form the counting function zeta sub u t. The t is a parameter again. Like up there, it's a parameter. What is it? Well, it is the sum of chi sub u composed t to the j. J goes from 0 to some m, and m, the cutoff time, is exactly the same one here, namely this parameter scaled by the measure of mu, the cut scaling. So what it does is zeta of n of t of x, anytime you get a hit here, you add 1. This simply now counts the number of hits you get on an orbit. So here's the point x. So if it travels around, so it's going to hit here, here, there 3 times. That would come in as a value 3. So that's the number of hits of the orbit segment of x up to time m. And in particular, of course, you have tau sub n is bigger than m. That's exactly the same to say that zeta u t of x is equal to 0. So you can rephrase this. Look at this is the 0 level set up there, what you're looking at. Right? The 0 level set has this size in the limit, if you put it that way. So why is this interesting? Well, the interest, of course, comes from this one, because if you look at the orbit and you note every hit you get, and if this return time here is, if they are all exponentially distributed and completely independent of it, like you reset the clock, once you arrive here, you reset the clock, and you restart anew, and you forget the past, then you would expect get a Poissonian distribution. So in the independent case, what you would get is the probability of the level set would go towards e to the minus t to the r factorial, which is Poisson. This kind of matches the independent case. Here, if there's a lot of independence there, then you get e to minus t. So if you get a lot of independence, you should expect Poissonian, which is a natural question to ask, but the answer is not obvious. You can't immediately deduce from this one, because you might have situations where you get around to some periodicity. Like, for instance, if you wait for the bus, the first bus comes pretty randomly. If it does go to the bus stop, the second one does not come in randomly, because you know it's going to be whatever, half an hour later, 15 minutes later. So that question was for the first time considered by Dublin in 1940. So this much precedes Katz's, or precedes several years, Katz's theorem. So what did he do? Dublin in 1940. Incidentally, this is the same. This Dublin is the son of the novelist Dublin who wrote Berlin Alexanderplatz, and it took mathematicians actually a couple of decades to find that one out. So he looked at the Gauss map T, which goes from 0, 1, or maybe included 1, to 0, 1. And is defined by the fractional part of 1 over x, which is 1 over x minus the integer part. Has infinite many branches. So you can also, of course, write x in a fractional expansion, a0 plus 1 over a1 plus 1 over and so forth. That's the fraction, the continuous fraction expansion. And, or you can say 1 over x mod 1. This is better, because this one picks out what the an is. So what you get is, you get the aj is 1 over tjx integer part. So this is aj of x, because these guys, of course, depend on x. A3 of x. So you see, the a0 is, as you would expect, well, the a0 is the 1 over x t to the 0, and you take the integer part of that, and once you've walked your way down, that's what you get. So what Dublin proved was the following thing, that if you look at the probability of this set, look at the size of this set, where j is less or equal to some index n, and you want to have ax being bigger than 1 over t times n times t over log 2. So which means this an is aj are going to be too big for some number of times. Count those. If there are, how likely you find r of those sitting in there? This goes towards e to the minus t to the r over r factorial. Now if you look at the ar here, what you see is, you see that tj of x is, what is it? Well, you reverse this one, you get 1 over aj of x plus 1 over aj plus 1 plus 1 over and so forth, which means you get roughly 1 over aj plus big O of 1. So it's about 1 over aj, never mind the big O of 1. So you have that aj is going to be bigger than some number m if tj of x lies essentially in the interval 1 over, in the interval between 0 and 1 over m. So we can call this one a sub m. The measure of this a sub m is, the Gauss measure has the density, which is 1 over log 2, 1 over 1 plus x. We are close to 0 there, so this is about 1 here. So you get 1 over log 2. So you get, this is 1 over m log 2. So now if you rearrange it, what Dublin showed was that the probability that tj, that the number of t are equal to r goes to e to the minus t, t to the r factorial as m goes to infinity. So m in that case up there, you do a change, m is equal to n over t log 2. So therefore you get the scaling, the cut scaling, which is, so you get n is equal, n tells you how far you're going to watch it, right? That's the orbit x segment you look at. So it's t log 2, t over n over log 2, which is t over mu of am. So this is exactly cut scaling. So this is Dublin's result from 1940. So he has proven the Poisson distribution at the origin for the Gauss map. Then we had to wait till dynamics, at least we had to wait till 1990, till Pitzker shows up and proves the Poisson distribution is in the limit Poissonian. If we look at cylinders for axiom systems and equilibrium states. So there's a theorem here. Pitzker, well, he errated to some degree. Then, well, there are a lot of quite some names attached to that one. Maybe I shouldn't forget too many of those. Abadi was in there too later. Rani. Well, I hope I didn't forget anybody. So roughly what happens is this. You take a cylinder and you look at the counting function for a cylinder. You look at the level set of that. This goes to e to the minus t, t to the r. R factorial as n goes to infinity. As n goes to infinity. We might have to have slight changes of t. You get also error terms. So this is psi mixing, phi. I think Abadi and Vernier, they have a combinatorial argument to do it actually for alpha mixing as well, and also for these three guys here. For this parabolic map, Pomovian-Manville map, which has a parabolic point here in a finite measure, so alpha less than 1. Then we can also do this for unions of cylinders, and in this case an can actually be, in the sigma algebra of an, one has to have certain decay rates, of course, that the measure really goes to 0, which has to do with the mixing rate, and one also needs a condition, a short return, plus a short return condition. So one can play this game a little bit in more generality. This uses Stein method, and as a corollary of that, incidentally, rather interesting, because the short time condition, if you just restrict it to cylinders only, so if you take an only a cylinder and not in the sigma algebra of these guys, and let the cylinders goes to 0, then the short-term condition, you know exactly what happens to that, namely, what happens in a non-periodic point, it goes off to infinity and is satisfied ultimately. So then you get that p of zeta of a n of x, t, equal to r goes to e to the t, t to the r factorial, no matter what, for all x non-periodic. If phi, in the phi mixing case. The zeta is the counting function. That's the counting function. I can write it down again, say over here. Zeta sub u von a bis z u is the sum of chi sub u. You now count the number of hits where you go up to some time m, and m is the rescale t by by the cut scaling. That's the counter. So let me talk about balls. Well, the original paper by Pittscore has a result for the torus, for two-dimensional, for axiom A on a two-dimensional area. So if I take, he says for torus. So this is 1991, I believe one of these. And then you get the same thing, that the probability of the zeta for a ball of t equal r goes to, let me just say, P of R, the Poisson distribution of R, as rho goes down to 0. He uses an approximation argument and approximates the ball from inside and outside, so he has the typical argument to have a little skin here to deal with. In two dimensions, because he had to control the directions, the two directions. That's why it's restricted to 2 dimensions only. There is a similar argument by Denker, Gordon, and Sharova, also in the torus. We use lots of harmonic analysis in Stein method. Then for T2, no, actually Tn, Tk, I believe. And then we got also for rational maps. And equilibrium states. The condition there is that the dimension, the Hausdorff dimension of balls is bigger than 1, because the difficulties one gets into the approximation argument there, because one wants to kill this. This has to be percentage of this, and has to go to 0 as it gets smaller. So there was this funny condition there that the dimension has to be smaller, and then one can go along a sequence, and not for any old. And then there exists a sequence rho n goes down to 0 for which one can do this. Then we have Chazot and Collet. Is the second one somebody here? Yeah, I forget now. Someone here. Anyhow, so this is, you have a manifold, you have an attractor. Attractor, codimension 1. Mu is the SRB measure. Well, the technique requires that you use Young towers, so you have to allow for the existence of Young towers. When you talk about Young tower, of course, you have to talk about the tails. And I will say something about Young towers just in a minute. The tails are exponential. Then you get that this function here, b rho of x equal to r, goes to the Poisson of r plus error terms plus big O of rho to some a for some a positive. On a set, well, because if one has error terms, one has to control, of course, where this is valid. On a set outside a set of size, big say, let's take the same a, or some other a, some a positive. So the one I want to talk about is the one is with Vasilevska. To get rid of in particular of the exponential tails, and to do it for polynomial tails. So for instance, you have the same setting. You have mu is SRB. You have Young towers. You can say an attractor if you want. Then you get the same thing. You get P of, and you get polynomial tails. At rate lambda, which means the tails, I will say later on, are of the order p to the minus lambda at least. Then you get that p of the counting function r is going to be, well, the Poisson term plus 1 over log. This times the convergence is logarithmic, where kappa is less than lambda minus 4 over 2. So we have to ask for lambda bigger than 9. So where does this one come from? This is outside a set of size big O of 1 over log, rho again, but this time lambda minus 9 over 4. Maybe it can be improved a little bit. So this comes out of a somewhat more general result. For which we need two conditions. Namely, we have to say something. You have to make an assumption about very short returns. So, put v of some a total, say, v sub rho. So what is the problem we have? Well, all these short returns, namely, these are all the points for which there exists an n, and this n shall go up, say, from 1 to some cutoff which is proportional to log. So that t to the n is going to lie in t to the n b rho of x intersected b rho of x is not empty. So these are the very short returns. That's why the v here. Very short returns. And the time scale is log rho, which is very small. So like in a cylinder case, it would be a multiple of percentage of n. So if you look at n cylinders, say anything that comes back to hundredths of n would be, like a twiddle would be, say, 1 over 100. So we want to have this be, we want to avoid this set here, and in the case of the attractive, we can actually estimate what this set is. The second condition has to do with the approximation. I will simplify it a little bit. So this is, let's assume that sigma is the dimension of the measure mu. And we have to request that this number, psi, which is sigma times lambda minus 2, yes, lambda minus 2 is bigger than 1. Bigger than 1, yes. Then, so the dimension shouldn't be too small. If the dimension is small, then lambda should be big to compensate for this, for the lack of size of the set. Then we assume there exists a W between bigger than 1, but doesn't have to be equal to psi, can be less, or should be less actually, so that, and now comes this analysis condition. So this is the analysis condition where you have to take this one here is exactly this with a thickness of rho to the W, and this one here is rho. So the skin you put on, you put a thinner and thinner skin, and you want to make sure that this one here is going to be less than a constant times, well, log rho to a power. Well, in reality, it's a little bit more complicated there, but we don't have triple trouble with that with respect to this one in particular. So this is a rather weak condition, because if in a Lebesgue case, then you have something way stronger than that. So if these things are satisfied, then we have the following theorem. So if lambda is bigger than 4, and again the lambda refers to the young tower decay, so this is the tails and the young tower. We don't need the 9 here, we need the 9 only to show that the V, this really exceptional short set, is short. But otherwise, if we just exclude this set, we don't have to worry about this very much. So then there exists a set x row in omega, so that, well, you get the counting function rho, t is r, is going to be, well, let's put p of r plus big O of 1 over log rho. Log rho to the lambda minus 4 over 2. This is where the 4 comes from. Outside x row, where mu of x row is of the size of 1 over log rho again. Now it's lambda minus 2, I believe. What is it? Yeah, let's take the same. Lambda minus 4 over 2. Isn't it? Okay. So we can control the forbidden set. And if I have time, I will say something about the forbidden set. But of course, the two lemmas that connect 1 to 2, or the previous statement to the theorem there. Well, the lemma we have is the first of the two lemmas I want to mention. So if now let's go back to the attractor case, where mu is the SRB measure, and let's assume it's SRB with the usual one with respect to Lebesgue and unstable manifolds. Then, well, and assume, of course, well, lambda is bigger than then. Now we look at the annulus. Well, this is the one we have to control, and what we get is that this is going to be bounded by a constant, and now what we get down here, we get a log rho, and now we get a w minus w naught, and this whole thing to the 8th power. Well, this technically plays a role, this w minus w naught, so I write it in just for the fun. But the important part, of course, is this one here, that you get the log rho. So this is for w bigger than w naught, which is, where am I? 2 over u, d plus 1 minus 1. U is the dimension of the unstable leaves, and d is simply a dimension of M. If you can do it like this, and A is any number less than lambda minus 2. So A is anything less than lambda minus 2 over 2. So lambda bigger than 2 is good enough in that case. The second lemma, so this is the lemma, that's the lemma you need in order to satisfy this condition number two right up there. This is a very classical, very standard condition on the annulus. You have to be able to compare it. The second one is if lambda is bigger than 9, then there exists an a twiddle such that v sub rho of a twiddle is big O of 1 over log rho lambda minus 9 over 4. All right, so these are the results, and so I still have some 10 minutes left, so I can say something about the young towers and the key lemma that actually enters there. I don't know whether we'll get much chance to see how it plays a role actually, but to get a rough idea. So the young tower is formed by some lambda in some m, which you decompose into a countable number of subsets in a disjoint fashion. Then, well, let me just do the expanding case. Let's assume just it's the expanding, make it a little bit easier. So I don't have to say about the stable manifolds. Then you have this return time function, which goes from lambda to r to n. And this return time function is constant on each of these elements lambda I. So you have this return time map, which is simply t to the r, which maps lambda to itself. So here's the construction. Here's lambda, and then you follow it through until you come back and map to the entire thing again. That's construction. And the return doesn't necessarily have to be a first return. This can be a later return, but it is one-to-one. So this one here, you map from this one by t all the back to the entire interval. The map on this tower, so this would be omega here, which mimics m, and the map on omega, which is the same, which sort of mimics the map of t, is simply going up. I want you just have a counter ratcheting up, an odometer till you reach the top, and then you're going to reset. Then you apply the map and you reset. Now the tail condition is the decay of this function as you get bigger and bigger. M hat is a given reference measure down there. Say, assume it's the Lebesgue measure in the attractor case. So M hat is so-called the reference measure, because everything is expressed in terms of the reference measures. You can have some other measure there, then you have to satisfy all the conditions on regularity and distortion and whatnot, and then you get an invariant measure which is absolutely continuous with respect to this, because you're looking for an invariant density. In the Lebesgue case, it's Lebesgue. This has to decay at some rate. So in our case, this is going to be k to the minus p. P is some k to the minus lambda. Lambda being this lambda up there. And in exponential case, it would be some number theta less than 1 to the power k. Now, under these conditions, other conditions as well, you get, then there exists an invariant probability measure, mu on omega. It has more structure than just being mu, because you immediately see what has to happen as you go up this. So there has to be something said about subsets on lambda here. Suppose it's lambda that lives in lambda I, then what happens as you flow up, the measure doesn't change. So the measure of a little set up here is going to be exactly the same. You just take it down and look where it came from as before it floated up. That's the measure of the setup there. So this is how you construct the measure. You actually construct the measure down here, and then you float it up and patch it together. And you use the fact that the integral of this return function is finite, which means the total volume of this is finite with respect to the base. But the point here is, you get exponential decay, you get decay of these correlations. You get g times, you push this one forward, you integrate, subtract averages. This behaves like n to the minus lambda minus 1, and then you get norms in here. Namely, the norms you get is, you get the the Lipschitz norm for G, and you get the L infinity norm for H, but not in the expanding case. It's okay, but the result is true in the non-expanding hyperbolic case. Then the H has to be constant on stable, local stable leaves, in the way that comes with the construction of the Young tower. In the general case, it has to be constant. And you take advantage of this, because otherwise you have to do an approximation argument, and then you have to pay for it by putting Lipschitz in here, and then things become, you can't handle them anymore because you have to pull back complicated sets. And there's no way you can control this. But with this approximation, you can actually manage. So I will say this key lemma and maybe give you a short indication about how it's used, how it's relevant. And with these Young towers, you can model a lot of systems. Haydn maps have been mentioned, so some rather unpleasant ones can become accessible suddenly. So the key lemma is this. Well, you look at the decay rate of these tails, and you kind of split this into two parts, and the favorite way seems to be you take the root of that. Okay, so let's take the root of that. Omega of S is the root of M of R being bigger equal S. So N and S are simply two integers, arbitrary integers. And you play with those, of course, as you go along. So you split this into two parts here, because it serves two purposes. Then what you get that, let me put it roughly here, then you define a set lambda twiddle. Now these are all the points x in, let's put lambda, suppose everything lives on the base. The other stuff is stuff handled by pulling things down and taking care of all these extra terms. But we cut out of this lambda an interesting part, which means we take out the part that is kind of doesn't suit us. The part that doesn't suit us is where you might have to go up a long time till you return. Of course, once you return, you get an awful lot of expansion, but that's not good, because you pick up expansion every time you come back, and that's what you want. You want to pick up lots of expansion. Throw away the tails. So which means R of t hat of x to the j is less or equal x for j from 0, 1, 2, up to some cut of n. This n we're going to cut off. This is our ceiling there. We're going to cut off the tower at level S. Throw away this stuff. How much do we throw away? So then, if we take the mu of, if we take this sum over all I over all j from 0 to Ri, so till we come back, and then the mu of t to the minus j of b rho intersected lambda twiddle complement. So these come back soon. The complement are those we want to throw away. That's the tails. Then this is bounded by mu of b rho times root of n times this omega function. If we are outside a set of size the same, root n omega s. That's the key lemma. What you do with it is, as you go along, well, I won't tell you the approximation argument, except that you're going to swap out one by one terms and replace them by independent terms. Then you have to compare. Then you have to compare what happens when you swap out one term. So you have all these j's sitting here. But you swap out one term by an independent term. So first of all, you're not going to watch for some period, say, delta. The very short ones we know don't exist, because let's assume we are not in the very short returns. We throw those away. We simply cannot handle those so readily. Then you have this gap. So delta is the gap. And delta is actually pretty long in this case. Namely, it is 1 over rho to the dimension, roughly, a little bit more than the dimension. And you then throw in a logarithmic term for good measure to some kappa there. So these guys here are the most difficult ones. So what you do here is correlation. You approximate. You have the skin, you control the skin, and you have a contest between, you want to make delta alone, you get lots of expansion from the curve correlation, but on the other hand, then if you approximate too well, then the delta becomes too bad, the norm gets too big. So you have a little contest going on, but you win it if you choose it this way here. But then you have these ones to deal with, and there's a lot between the a twiddle log time scale of this guy, because you close your eyes for this time, which is just a moment. But then you have to wait quite a bit until you come to this one, which is a huge number. This is nearly of the order, it's a little bit less than 1 over mu. You take, sigma prime is, what is it, less than sigma actually. So it's really less than the cut scaling gives you, but maybe 1%, but still huge. You have to deal with these terms. And what you come up against is you have to control these. And you have to estimate this in terms not by a crude estimate by simply saying mu of rho times the number. That's no good. You need a contraction. You can need a contraction making term times something small. The way you do that is, and this is where the tower comes in. This is t to the minus nb, say. You intersect with b rho. You approximate b rho by cylinders. So you have cylinders sitting here. And you have to make them small, because then you're going to take this t to the minus n, intersect it with the cylinder, and compare it to what this cylinder is. Because if you stick in a cylinder there, you get approximately mu of b t inverse nb intersected b rho. Right? If we take the sum over cylinders, that approximate b rho. That's what you get. This one here, you get is less or equal b rho by distortion and other things. So then you have this guy left, and this one here times a small term which makes contraction. This plus this sum has to go into there, because this term here we need. We need it for the summation over the entire time up to time m. And in order to make this guy small here, you have to know that this one is small. But how do you get it small? The metric on the tower is determined by how often you come back. Every time you come back, the closeness of 2 points gets a factor alpha. You have the distance given by alpha, and some number alpha less than 1 time to the power of the separation time. Separation time is when you come back and sit in different lambda I. So you have to count the number of returns. That's what the key lemma does. It makes sure that the number of returns is at least n over s. That makes this very small. So we know these guys are small. Namely, the diameter is less than alpha to the n over s. So therefore, this small term we can control, because it is given by essentially by the measure of the unions of all those guys. But we take the zeta that lie inside. So they might be a little bit big here, right? But we know that their diameter is less than L alpha to the n over s. So the convergent making term, this term gets killed. Did I say something wrong? Oh yes, I did say something wrong because I forgot half of it to write down. This is less or equal mu of b rho times small term. This is a convergent making term which comes from here, plus the sum. This convergent making term is like the diameter, all of course you have the ball sitting here for radius rho, but then you have these things sticking out, but they're not going to stick out more than alpha to the n over s. So you get plus alpha to the n over s. So this is like rho plus alpha to the n over s to the dimension, something like this. Now all you have to do is, why don't you choose s like a power of beta? Then this becomes a stretched exponential decay, right? You get n to the 1 minus beta. These guys you can add up to lambda, to delta, to the gap delta. There's no problem with that because the first term is the dominating term because it's stretched exponential. So this is how you get the convergent making term. And that's the key lemma for it to make it. Then you have to control all the other soft technicals and optimize the coefficients. And yeah, thanks very much.